In this video, guys, we're going to go ahead and prove the third kinematics equation, v final squared equals v initial squared plus 2 times the acceleration times the displacement in the x direction. And we're going to make use of the first two kinematics equations which we proved in previous videos. So we proved v final equals v initial plus at in one of our previous videos. So what we're going to do is we're going to go ahead and square both sides of this equation. So we have v final squared equals v naught plus at times v naught plus at. And we're going to go ahead and FOIL this out. So I'm going to show every step so that you guys can follow along. So we have v naught times v naught, which is v naught squared, v naught times at, which is v naught at times v naught, which is the same v naught times at, and then at times at, which is a squared times t squared. And we can write this as v naught squared plus 2 v naught at plus a squared t squared. And we can go ahead and rewrite this as v naught squared plus 2a. I'm going to factor that out there. So I'm looking at these two terms here. So if I factor out a 2a from those two terms, we're left with v naught t plus 1/2 at squared. Now you can go ahead and verify that this does in fact give me those two terms there, because 2a times v naught t gives me 2 v naught at, and then 2 times 1/2 gives me 1, which is the coefficient that I have here, 1. And then a times a is a squared, and then times t squared, so we're left with 1 times a squared t squared. Now you'll notice that what we have in parentheses there, the v naught t plus 1/2 at squared, is actually the displacement in the x direction, which is actually the second kinematics equation. So we're left with v final squared is v initial squared plus 2 times acceleration times the displacement in the x direction. Now keep in mind that this is the third kinematics equation, and since it's a kinematics equation, it can only be used if the acceleration is constant.